So we're going to start with sequences today. The rest of the chapter we will cover next week, Tuesday. Okay, and then this will be the second part for your test coming up. Okay. So remember the test, conic sections, sequences series, Taylor series. So this will be the second part for that. Okay, so definition. A sequence of real numbers is a function let's call it A. Okay. And there's still too much talking. There's a function A from the natural numbers to the real numbers. Now you get different types of sequences. So you get sequences of functions, sequences of real numbers, sequences of integers, and so on. We will be dealing with real number sequences only. Okay, where we take a natural number n and map it to some real number, which we call a sub n. Okay, this little a sub n is just some notation. Notation for a of n. Right, like we have a function f, we write f of x. For sequences, we don't write a of n. It's just a convention. We write a with the little subscript n. Okay, and then an important note here. The set of natural numbers that we have there, n, we will take to be starting from 1. Right, there's debates on whether natural numbers start from 0 or 1. We will start from 1, so that avoids any issues if we see 1 over n. Right? So if I don't make this clear, you might think natural numbers start from 0. Right? Some people take that. But then 1 over n becomes an issue. Yeah. So we will always take the natural numbers to be from 1. Okay. It avoids the issues with the 1 over n, whether it's 1 or infinity or whatever. Okay. Just some notations on this. Okay, now again, it's just notation. You can pick whatever you like. So the first notation for a sequence is just A1, A2, A3, dot, dot, dot. So we just list out the elements. So A1, that's when n is 1, so that's your first element. A2, that's when n is 2, so it's your second. And we just list it out. That's one notation. The second notation is we use those set brackets. So we have A1, A2, A3, dot, dot, dot. And then we just put the sequence in a set like this. So this doesn't mean set, it means sequence, right? They're very different. It's just a notation. Another notation is you just write it like this. So you have an, whatever that may be, and then you put the set brackets. You might see that. And then something a little different from that is we have an, and we say n goes from 1 to infinity. Again, it's just notation. It all means the same thing. We're going to be using that first one. Okay. So I'm just going to list them out. We're not going to put the brackets or anything. But I mean, you can feel free to use the other ones, but we will use this one. Okay. Any questions on the notation, what you should use, what you shouldn't use? Oh, fine. Okay. The limits of a sequence. Definition. The limits of a sequence, sometimes called the limiting value of a sequence, or limiting point. So limiting value, limiting point, it all means the same thing. Of a sequence a sub n, whatever that might be, is given by the limit as n goes to infinity of whatever this a sub n is. So we have some sequence of real numbers. When we take the limit as n goes to infinity, if we get some value, we call that the limit of the sequence, or the limiting value, or the limiting point. It all means the same thing. Sometimes we drop the n goes to infinity because it will always be limit n goes to infinity. So you might see this written as just lim an. Because we know it will be n goes to infinity, so we don't include that. So you might see that. Okay. A few more definitions. If this limit exists, we know how to test for that, if the limit exists or not. If this limit exists, then we say that the sequence converges. It's just some terminology. So if the limit exists and we get a value like 2 or 3 or something, then we say that that sequence converges. Otherwise, it diverges. It's always one of the two. It either converges, where the limit exists and has a value, otherwise it diverges. It's always one of the two. Let's have a look at some examples. So number 1, we have an equals 1 plus 1 over n. Okay. So now we want to take the limit to see if this exists or not. So when n goes to infinity, what happens to the 1 over n term? It goes to 0. Yeah. So when n goes to infinity, 1 over n goes to 0, and we're just left with 1. So here we can see that the limit of an is just 1. Okay, so the limit exists. Therefore, the sequence here converges. Okay, example 2, root n. Okay, so we're looking at root 1, root 2, root 3, root 4. What happens to this sequence when n goes to infinity? So root 1, root 2, root 3, root 4. What happens in the limit? Diverges, yeah, goes to infinity. So here, this one, the limit doesn't exist, it diverges. Okay, and example 3, an equals sine of pi over 2n. Okay, we want n goes to infinity. So let's see what happens. When n is 1, we get sine of pi over 2. What is that? Special angle, 90 degrees. It's 1. And then let's say n is 2. That's the next one. Sine of pi, 0. And then when n is 3, sine of 3 pi over 2, negative 1. And then we go back, sine of 2 pi, 0. And then it repeats, right? As we go. So it will be 0, 1, 0, minus 1, dot, dot, dot. Does this have a limiting value? Think about it. Does this have a limiting value to it? No, it doesn't. It's alternating. So we have 1, 0, minus 1. then back to 0, back to 1, back to 0, back to -1. Right? It alternates between those three values. Now, it's continuously alternating for every n going on. It keeps alternating. So this diverges. Remember, it can only be converges or diverges. If something is alternating and it never settles on a limit value, we still say it diverges. Even though it doesn't go to infinity, it still diverges. So here, this alternates forever. So no limit value. Okay. Think about what we had before last year. Limit x goes to infinity of sine x. Right? Sine x alternates between +1 and -1. That limit did not exist, right? So in this case, we have a similar thing. The sequence alternates between 1, 0, and -1. It alternates forever. So the limit does not exist. So it must diverge. Okay, so please be careful about this word diverge. Diverge doesn't mean that it goes to infinity. That's one case. Another case is when it's alternating. It also diverges. So please just keep that in mind. Any questions about converges or diverges? Okay. We're going to do a quick recap of the limit laws. So it's all of the stuff we did last year with limits. Most of it carries over to sequences. Yeah, so I'm just going to write down the limit laws. It's very similar to what you've seen before. So limit laws review. Okay. So last year when we did limits, we had limit laws for f of x and g of x and so on. And we used those limit laws to evaluate limits. We're going to do the same thing here, but instead of f of x and g of x, we're going to have sequences. But you'll see all of these are the same as last year. And it's not working today. Before I forget the register, previous processor. The register is going around. Please make sure you sign it. Okay. Okay, if AN and BN are convergent sequences, okay. So remember before when we had limits of functions, we had f of x and g of x, and the limit as x goes to a of f of x, and the limit x goes to a of g of x exists. Right, we had that last year. We have a very similar thing now, but instead of those limits existing, we have sequences that are convergent. But we know convergent means the limit exists from before. So there's a few laws here. They should look familiar to you. So we have the limit of an plus or minus bn is equal to the limit of an plus minus the limit of bn. Again, both of those must be convergent. Number 2, the limit of some constant times the sequence. This constant can come out. Number 3, we have the limit an times bn. This becomes the limit of an times the limit of bn. Okay, number 4, we have the limit of an divided by bn. This will be the limit of an divided by the limit of bn. But as we had before, that bottom part can't be 0, right? So here, the limit of bn can't be 0. Okay, and number 5, we have the limit of f of an is equal to f of the limit of an. What's the restriction on f for this last property here? It can't be any f. It must be a particular type of function. Remember from last year? It doesn't work for any function. It's only there's a certain thing it has to satisfy. Being quiet. How about an extra 3 points for the quiz next week? F must be blank. What did you say? Continuous. Very good. Get an extra 30% next week. Somewhere in the top there. Okay, very good. F must be continuous. Okay. Right? If f is continuous, the limit can go inside and outside, right? So here f must be continuous. So if f is continuous, the limit can jump inside here. Okay. So a limit on the outside can jump inside, so we have f of, and then the limits on the inside there. Good. Must be continuous. Okay. Did you put your details? There'll be answers for the rest of you to get some points. Any questions on the limit laws? Okay, again, this is just straight from last year. Nothing new with this. Any question? Oh, good. Okay. So again, that's just from last year. It was a quick review. Now we get to the new stuff with some important theorems. Okay, so these theorems, we'll do the proofs for some of them. Okay, the ones that we do the proofs for, please put a little star. You'll need to know that for tests and exams. The ones we don't do the proofs for, you can leave that proof out. Okay, I won't set that for homework or anything. So it's important to know the theorems, of course, for proofs and stuff, but this will also be very useful for calculations. Okay, so theorem number 1. If the limit as x goes to infinity of f of x is equal to L, here when I write x, this is last year calculus, right? With the x. So if limit x goes to infinity of f of x is L, and f of n equals a sub n, then the limit as n goes to infinity of a sub n is also L. Okay. Looks a bit confusing, but once we draw the picture, it will make perfect sense. So let's draw a little sketch of a sequence a sub n, and then we'll see what this f has to do with it. Okay, so we're going to have 1, 2, 3, 4, 5, and so on. So when n is 1, we're going to have some value. When n is 2, we have some value, and so on. So if we want to draw the sequence, it's just going to be a bunch of dots. Okay, maybe it looks like that. So those collections of dots there, that makes up our sequence, right? We have A1, A2, A3, A4, A5. And that's our sequence. What this theorem tells us is that if there's a function, f, that agrees with our sequence on the integers, then they have the same limiting value. So f sub n is equal to an. What does that mean? It means it agrees with our sequence. In other words, if we connect the dots, we get a continuous function, f. So it will be something like this. Okay. We see that at our sequence values, 1, 2, 3, 4, 5, the function agrees. It passes through all of those points, but f is continuous. Yeah. Does everyone see that? So it's a continuous function that we can draw through the sequence there. That's what this means over here. Okay. It matches at n equals 1, 2, 3, and so on. Between n equals 1, 2, 3, and so on, the function can do whatever, but at those points, it must agree. Yeah. And then what does this tell us? It tells us that if you calculate the limit of the continuous function f, it matches what we have for the sequence. So let's look at an example. Let's say we have a sub n is n e to the minus n. And we want to take the limits of the sequence. Now, if we go back to our limit laws, none of these limit laws is going to help us, right? Because if we look at the problem, the first part here, n in the product, that diverges, right? When n goes to infinity, that diverges. So we can't use any of these product laws or quotient laws or anything here because that n diverges. It's not going to work. So instead of using the limit laws for sequences, we're going to convert this to a function and use the limit laws and squeeze theorem and L'Hopital's rule and all of that for functions. So we convert this to a function. Okay, so instead of n, we put x, the continuous variable. And now that we have a function of x, we can use everything we learned last year about limits of functions. So the limit laws with functions, L'Hopital's rule, squeeze theorem, all of that we can now use with f, which we couldn't use with the sequence. Right? Like L'Hopital's rule. How do you do the derivative of a sequence? You can't do that. But if it's a function f, we can do the derivative. So we can use L'Hopital's rule. So we can't use L'Hopital's rule on sequences, right? Because it's n equals 1, 2, 3. There's no derivative for that. But we can use L'Hopital's rule for functions. And what this theorem tells us is that whatever we get for L'Hopital's rule for functions is exactly the same as if we did it for the sequence. Okay. They both have the value L. So for this example here, we can use L'Hopital's rule because that's an indeterminate form. What type? Oh, hands up if you know the type of the indeterminate form. Sorry? No. Anyone else want to guess for extra 30%? Sorry? Yeah, very good. I get 3. It'll be 3 for all of them. Yeah, so when x goes to infinity, that first part there with x, that will be infinity. But that exponential part, that's going to go to 0. Right, so we have infinity times 0. Well, if you want to write it the other way, infinity times 0, it's fine. Okay, so it's an indeterminate form of infinity times 0. So what do we need to do before we can use L'Hopital's rule? Yep. Yeah, so x for the numerator, yeah, and then? Yeah, very good. Extra 30% for you. All you have to do is answer. It's not that difficult. Good. Good. We need it in that fraction form, the infinity over infinity or 0 over 0. So it's that pre-step to L'Hopital's rule. So this will now be infinity over infinity. So we can use L'Hopital's rule. Okay. I shouldn't have to reteach that. You covered all of that last year. So now we can do the derivative because it's just x. So the derivative of the top, that's 1. Derivative of the bottom, it stays the same. So this is going to be limit x goes to infinity, 1 over e to the x. What will this be? 0, yeah. Okay, no points for that. That's too easy. Yeah, bottom goes to infinity, goes to 0. Very easy. But now the theorem tells us that the answer we get for this function is the same answer for the sequence. So if you get 0 for the function, you get 0 for the sequence. Therefore, the limit n e to the minus n is also 0. Okay, so a very important theorem. It allows us to convert sequences to functions. Once we have the functions, we can then use calculus. Okay. So we got L'Hopital's rule, squeeze theorem, all of that stuff can be used. Okay, you can go back and forth between them. Right. Any questions for theorem number 1? Yeah. Number 2. Notice we didn't do the proof for that. So if there's no proof, right, there's no proof for the test. However, this one, there is a proof. So if the limit of the absolute value of the sequence is 0, then the limit of the sequence is also 0. Okay. Very nice. Now this comes with a very important note. Damn pen. Okay. The important note here is that this only works for 0. Okay. So we have the limit of the absolute value is 0. Then the limit of the original sequence is also 0. But if it is non-zero, this does not work. Okay. And we'll see an example with that. If the limit of the absolute value is some L that is non-zero, then the limit of the original sequence might not be L. Could be L, but it's not guaranteed. So please make an important note for that this only works if the limit of the absolute value is 0. Okay, so we will look at an example and a non-example, so where it works and where it doesn't work. Let's say we have an is minus 1 to the n over 1 plus n. If we were to use just our limit laws, that's not going to help us. Why? Because we have that minus 1 to the n. It makes it alternating. Right, and we know if it is alternating, we can't use that limit laws. Okay. Right, because it might be divergence. However, if we convert this to the absolute value of a sub n, okay, the absolute value removes that alternating behavior. So it's no longer minus plus minus plus. That minus 1 to the n, that goes away. Okay. What is the limit of this absolute value sequence? 0. Right? When n goes to infinity, that will become 0. So by this theorem, we know that the alternating sequence will also be 0. And again, we couldn't have used L'Hopital's rule or squeeze theorem or anything. So this is a good case for this theorem. Therefore, the limit of the original sequence is also 0. Okay, so a very nice trick that we can use when calculating. Now for the non-example where it doesn't work. Let's say we have an equals minus 1 to the n. It's also alternating. Okay, so you might think, okay, we can take absolute value. We can see what's going on. The absolute value of this is absolute value of minus 1 to the n. What's that going to be? Absolute value of minus 1 to the n. What does absolute value do? Gives you the positive. So what's the positive of whatever's inside? 1. So here we have the limit of the absolute value is 1. Now you might think, okay, if the limit of the absolute value is 1, then the limit of the original sequence is also 1. And we'll see that's not the case. What's the limit of the original sequence? Does not exist. When n is 1, it's going to be minus 1. When n is 2, it's going to be 1. Then it will be minus 1, then 1, then minus 1, then 1. It alternates forever. There's no limit value. So the original sequence diverges, but the absolute value 1 converges. So we cannot use the theorem in this case. So an diverges, and the absolute value of an converges. So we can't use the theorem. So this over here, it only works if the limit of the absolute value is 0. Okay, if that is non-zero, this does not work. Okay, so please put a big box around this. Yeah, so you can't use it everywhere. Any questions for theorem 2? You're good. Okay, let's have a look at a proof for this. Okay, again, some of them will have proofs, some of them won't have proofs. If I write down the proof, it's going to be testable. So what we want to do is show that if the limit of the absolute value is 0, then the original one is also 0. And we're going to prove this via the squeeze theorem. So we know that the sequence a sub n is less than or equal to the absolute value. Right? Because the absolute value is always positive, so it must be larger than whatever value we have. Okay, make sense? Okay. then a sub n will also be larger than minus the absolute value. Right? Because minus the absolute value will always be negative. So it's larger than that. So we see we have it bounded between those two absolute values. Now that sets up for squeeze theorem. We can do the limit throughout and then check. The limit on the left side matches the limit on the right side. Then that's the same as the limit of the middle. Right? Squeeze theorem from last year. So let's set it up. We have the limit of minus absolute value a sub n is less than or equal to the limit of a sub n less than or equal to the limit of the absolute value of a sub n. Standard squeeze theorem. You put the limits throughout. Now, for that first term, we've got the minus inside the limit. That's fine. We know constants can come out. So we can take the minus outside. Less than or equal to the limit of a sub n and the limit of a sub n. Okay. Now, what do we know about this left side and the right side with those limits? The one on the left and the one on the right. What do we know? It's 0, right? Limit of the absolute value of a sub n is 0, right? That's given there. Okay. So limit of a sub n is 0, right? That's given. So if the left limit and the right limit are both 0, what does that mean for the middle limit? It's also 0 by the squeeze theorem. Yeah. I hope you remember squeeze theorem from last year. It's going to be used quite a lot for these proof type questions. Right. Any questions for the proof? You're good. Okay. Then the last theorem for today, theorem number 3. This one's very important, so it gets a name. The subsequence theorem. Okay. The previous two, they don't have names. This one is quite important, so we give it a name. Okay, if the sequence a sub n converges, okay, so we can test that if it converges or not. Converges to L, some limit value, then every subsequence also converges to L. Okay. Very powerful theorem. So if AN converges to L, then every subsequence also converges to L. Okay, now we know what a sequence is. What is a subsequence? So a subsequence of AN is a sequence, let's call it Bn, which is given by A, and then instead of n, we have f of n. Okay, so what does this do? We have some function of n. This function of n picks out certain elements from the sequence and puts it in the subsequence. So here, this fn picks out certain elements from the sequence. Okay. We'll see a couple of examples. We'll make this all very clear. So, example, let's say we have an equals 1 over n. Now, I'm going to look at the subsequence of this given by bn equals a sub 2n. So here the function is 2n. So what does this do? Okay, so let's see what an looks like, and then let's see what this 2n at the bottom does. So an. So we're going to have n is 1, n is 2, n is 3, and so on. So this will just be 1, a half, a third, quarter, a fifth, and so on. But now we're not looking at n, we're looking at a function of n given by 2n. So a sub 2n, what's that going to be? So when n is 1, we're looking at a2, which will be a half. I'm going to leave some spaces here, but they're not really there. When n is 2, what am I looking at? N is 2. We get 1 over 4. Okay. And then when n is 3, 1 over 6. And so on. We see that this 2n at the bottom picks out all of the even terms because it's 2n. Okay. So here we pick out the half, the quarter, the sixth, and so on. That is a subsequence. We took the original sequence, 1, half, third, quarter, fifth, 1/6, and so on, and we selected out the even ones. That makes it a subsequence. Does everyone see that? Okay. Let's look at the second example. bn equals a 2n minus 1. So now the function, so now the function at the bottom there is 2n minus 1. So again, we go through, n is 1, 2, 3, 4, and we see what gets picked out. So when n is 1, what are we looking at? 1. When n is 2, 1 over 3. Next one. 1 over 5. And so on. We see that this function, the 2n minus 1, will pick out all of the odd terms. So 1, a third, a fifth, and so on. Okay, and then the 2n, that picked out all of the even terms. So we had the full sequence an, and depending on what we put at the bottom there, the first example picked out all of the even terms. The second example, that picked out all of the odd terms. And you can change the function to select whatever you want. Okay. Maybe you want the first one, then the third one, then the fifth one. You can make that function at the bottom there, whatever you want. So again, this bottom part here, this fn, picks out the terms that you want. Yeah, so if it's 2n, that gives you all of the even terms. 2n minus 1, that gives you all of the odd terms. You change it for what you need. Okay, so again, back to the theorem here. If an converges to L, then every subsequence converges. So if I give you some sequence, right, and I'll ask you, does it converge or not? If that sequence is a subsequence of something that we know converges, then it already converges. for example, in these two cases, does AN converge? 1, 1/2, 1/3, 1/4, 1/5, it converges to 0. So without even checking anything, A sub 2n, so a half, a quarter, a sixth, an eighth, that also converges. You don't have to check anything. We know already. And then the next one, 1, a third, a fifth, a seventh, a ninth, immediately converges. No checking required. Okay. So if you know it is a subsequence to a convergent sequence, it converges. You do not need to check anything else. Okay, so important. If you know AN is a subsequence of a convergent sequence, then it converges. Yeah. Any questions for this one? All clear. Okay. So that was the last of the major theorems. We're not going to do the proof for this one either. Okay, so it was just that second one that had a proof. Now for homework, you're going to prove a few more things. Okay, so just a note for tests and exams and so on. This section will be split into two parts. So the first part will be calculating limits. Okay, so I'll give you a sequence and the question will be find the limits, right? Standard calculations. The rest of the section in the test and the exams will be on proofs. Okay, it will be split between the two. Okay, so maybe 5 marks limit calculation, 10 mark proof. It will be split, something like that. Okay, so please make sure you go through the proof homework. Okay, so proof type problems for homework. Okay, number 1. I'll give you some hints for these, so you're not completely lost. But you should be able to figure these out because the ones you get in the test and the exam and so on, it could be seen or unseen. Yeah. So if the questions out of 10, maybe one of the questions is seen, like in the lectures or tutorials or something, the other one will be unseen, guaranteed. Yeah. So it wouldn't be in lectures, tutorials. I'll find something that you haven't seen. If AN is convergent, then prove that the limit of AN plus 1 is equal to the limit of AN. And I will give you a hint. Look here. Yeah. So what is that hint hinting? Subsequence. Very good. Okay, no points for that, sorry. Yeah. Yeah. You can use the subsequence because that bottom part, F, is just n plus 1. So if we know that A sub n plus 1 is a subsequence, we're done. You don't need to check anything more. It's already convergent. And we know what convergent means. Limits exist. Okay, so you can fill in the details for that. Number 2, if the limit of AN is 0 and BN is bounded, and here bounded, not convergent, bounded, Okay, it's important. There is a difference between the two. Is bounded. Then the limit of an times bn is 0. Yeah. And then for this bounded part here, I'll give you a hint. So when is a sequence bounded? Or when is a function bounded? You know what bounded means? So when is a function bounded? Function is bounded when it's smaller than some upper value and larger than some smaller value. Right? Like sine and cosine. It's bounded between -1 and 1. So here we have m is less than or equal to f of x less than or equal to capital M. It's bounded between the two. Think sine and cosine. It's bounded between -1 and 1. So if the limit of an is 0 and bn is bounded between 2 points, then show that the limit of the product is 0. Now, if we know that it's bounded, what can we use? Yeah, I will give some points for that if you figure it out. Squeeze theorem. Very good. Oh, you got points ready. Okay. Yeah, squeeze theorem. Because we have something less than something less than something else, we can use the squeeze theorem. Very good. So it's a small hint. Obviously, you need to fill in the rest of it, but that's your hint for number 2. And then number 3 for homework. Let f be continuous. Okay, we know what that means. And let a be a real number. Any number, a is free to be anything. Then we define the following sequence. So a1 is just a. So whatever number we pick there, that's what we start with. a1 is a. a2 is f of a, but we write it as f of a1. Right? But a1 is just a, so we can write this as f of a. a3 is f of a2, but a2 is f of a, so we have f of a. Right? So it's always the function of the previous thing, and so on. Okay, so that's the setup. We have this following sequence here, given some a and some f. So prove that if the limit of an is L, so we know what that means. If the limit is L, we know it's convergent, converges to L. Then f of L is L. Right? We don't know anything else about this function. Right? F is just continuous, right? We don't know anything else. But we do know from this proof here is that f of L is L. Okay, last 3 points for today. What is the hint for this problem? You don't have to give me steps or anything, but there's something that we need to use to get that. Sorry, he was first in the back. Yeah. Okay. Yeah, we got the sequence. Not quite. Not quite. Yes. The last one. This one. the continuity. Yeah, very good. Because we know f is continuous, so we can use that limit law. Right, so this one underlined in pink there. To use this limit law where the limit jumps inside, f must be continuous. So what we have over here is f of a1, f of a2, f of a3. What am I doing? I'm taking the function of the sequence. So I'll put it in pink here. So f of a1, f of a2, f of a3, it's the function of the sequence. I have f of an, right, for one of those. And we can see from our limit law, the limit can jump inside that. Okay. So very simple. You just start with that couple lines to fill in the details. Okay, good. So that's your hint for this one. Any questions for the homework? You're all good. Okay, so the quiz for next week, the MCQ part will be on this first bit with the limit laws, L'Hopital's rule, and squeeze theorem. Right, the three things we use to evaluate limits. That will be for the MCQ. So it's just matching the sequence to its limits, right? Using those laws. And then the written part will be 2 proofs, 5 marks each. Right. Any questions for the quiz? You're all good. Okay. I'll see you next Tuesday.